Hello, welcome. I can see people are already logged in, so welcome if you're already waiting, you're here for the session. I hope we're all doing well, enjoying mostly the nice weather, which is great. Feel free to say hello in the chat as well, so I can see that. I think my live chat is just a little bit delayed, but hopefully I can start to see some of the messages coming through. So welcome if you're there. I'm just going to refresh my page. Oh, excellent. I can see the messages coming through. Lovely. Welcome, guys. Hope we're all doing well. How are we? Excellent. I'm just trying to check if I'm on a bit of lag with the messages. Right. Hopefully these slides will be added shortly. I'll just check if you can get access to them. So we're going to be looking at transformations today. And there we go. I think the slides are available there now. So if you could check out that you're able to access those there. I'm good, thanks. Yeah, I'm enjoying the nice weather and the half term, and we've got a nice topic to go through, which should largely be a recap. I've recently done this topic on Snap Revise on our drop-in sessions. I think it was yesterday we went through this. I went through this with a few students. It's a really useful and important topic, actually, and often underestimated at A-level. We're quite familiar with transformations from GCSE, but actually understanding it really carefully and being good at it in year 12 is so useful as we move on to some of the harder functions in year 13. We do things like the modulus function, reciprocal trig functions. So all these ideas will be really important that we look at today. Could you let me know that you can access those slides okay? Be great to hear. And thanks again for messaging to say hello, those that are already logged in and watching. I am going to share my screen with you now, so hopefully this will be nice and clear. Right, here we go. So we're looking at transformations. Brilliant, that's good to hear. And transformations, here we go. So hopefully you can see that screen and we'll be good to go. I'm just going to make sure I can still access the chat and see what you guys are writing. So we're going to look at transformations today. So this is functions and graphs. And as I said, should be largely familiar, but a good topic to review and also ask questions as we go. Brilliant. Right, here we go. So let me get my pen ready. Lovely. Right. So flip that round. Transformations. Here we are. So as usual, at the end, I will be giving away the code for the discount for Snap Revise. So stay tuned for that. If that's something you're interested in, that would be brilliant. And let's have a little look. So here we go. So we're going to look at this question together. Feel free to work ahead of me, give this a go if you've got access to the slides already. So we've got a function drawn out for us. Looks like a kind of negative cubic, but they've not told us the equation. They've just called it f of x. So we're told the points that it passes through, 0, 3, 4, 0, and 1, 0. And then it says on separate diagrams, sketch the following curve. So we've transformed it here and they've explained it in terms of the function y equals f of x plus 1 inside the brackets. Brilliant. If you could send your suggestions in, that would be superb. Let's have a little think about what happens here. So what is this transformation basically describing? What is happening here? So very like GCSE in that if you just describe the points, you can kind of fit it to that shape. Absolutely. What is going on with this one? Cool. So let's have a little look. I do agree that those points that we've suggested there are moving in the correct way. We are moving one to the left. So this is a translation. One to the left. Because inside the brackets, we kind of do the opposite to x. Absolutely. Brilliant. Well explained. So basically those points, as some of us are suggesting, are going to just move over by 1. So it's going to move to the left by 1. And this point here, no, not there. Here it will now go through the origin. And it will have the same shape. And this point here absolutely will be the point 3, 0. It will go through 0, 0. And this point that was the y-intercept, perhaps slightly less significant now, is at -1, 3, absolutely. But it actually only just said on separate diagrams, on each diagram show clearly the coordinates of all the points at which the curve meets the axis. But you're probably used to, from GCSE, just stating where all the points go that are originally listed in the original function. But as it's a sketch, I would probably make sure that the shape is correct and that the kind of intersections with the axes are in the right place. Is this one clear? Is this something we recognize? It looks quite reassuring from the chat that we know what's kind of going on here. So inside the brackets, we're kind of doing the opposite to x. And then outside the brackets, we just kind of do what it says to y. So is that clear? Is that something we're familiar with? Brilliant. Right, that's nice and reassuring. So let's keep going then. And as I said, hopefully you've got access to the slides. So if you want to work ahead, that's brilliant. Excellent. And welcome to anyone that's joined in the last few minutes. This should be a nice recap largely, but we'll go through it now. So here we go. So this one says, for that same original function, sketch the curve with equation y equals 2f of x. So what are we doing? What is that 2 doing to the function? What is the point of this transformation? Any suggestions what we're doing here? Superb. So we've got some suggestions in already. Absolutely. That looks great. And let's check we all agree. So what kind of transformation has this function undergone? Brilliant. It's a stretch in the y direction by a factor of 2. So all the outputs of the original function are getting multiplied by 2. So essentially all the y values are being stretched by a factor of 2. So this point that was 0, 3 is now up at 6. And essentially it's the same shape, whoops, but it's now just been stretched in the y direction. So this would be doubly as high, but we weren't told what that point was. That is not the best sketch, but hopefully you can see what I'm saying there. This will still be 1, 0 because it would be the 0 that's stretched. So that stays at 0, and this would still be 4, 0. Does everyone agree with that? Is that something we recognize from GCSE? And this is an important point because actually it ties in with some of the stuff we've done in the earlier chapters of year 12. So for example, if you're given a quadratic graph, imagine you've got y equals x squared plus 2x plus 1, and then we have the graph of 2x squared plus 4x plus 2. What's really interesting about this graph is that you'd have the same solution at 0, but it would be more stretched. So the zeros, the roots, the x values don't change, but obviously the y-intercept and anything that essentially has a y value other than 0 will double. Excellent. So that's really reassuring and good to see. Brilliant. Great work there. So that's a stretch parallel to y. That was nice and straightforward, hopefully. And something we've seen in lots of different settings, not just from these kind of polynomial cubic graphs. Right, let's have a look at another question here then. So this is, again, another transformation of the same graph. What happens here? What are we doing with this one? And again, it is nice to try and make the link to other functions that you know. Like if you knew the equation, what would you basically be doing to it? So understanding it from a transformation point of view is great, but also understanding why that happens is really crucial as well. So do tease that idea out. So what goes on here? F of a half x. Again, it is something that's sort of tested at GCSE, but it's something that we'll build on. Right, a good suggestion. It's not quite the same. It is in the x direction, and it is some sort of stretch, or the other way around. But oh yeah, no, it is. It is absolutely. I'm getting confused. It is stretched by 2 in the x direction. So because it's a half, you do the opposite to x. So dividing by a half is essentially timesing by 2. Brilliant. So all of those x points that was at 1, 0 will now be at 2, 0. Well done. And the one that's at 4, 0 will be at 8, 0, as some of you, I think, have suggested. So it doubles the x values. Well done. So it's a stretch by 2 in the x direction, absolutely. So what will happen to the y-intercept, the 0, 3 point? I think someone has already suggested this. Looks like Thomas has already suggested what happens to that. That will stay the same because 0 being multiplied by 2 or anything happening to 0, that's still going to stay as 0. So nothing happens to that. Excellent. So that will still stay at 0, 3. And essentially what's just happening is they're kind of, if you were to do it on the same axes, they're getting more sort of spread out. Okay, it's getting kind of stretched parallel to x. Brilliant. Well done. So that point as well, we should clearly indicate is 0, 3. So the y-intercept stays the same. That is superb. Brilliant. Right, it looks like we're pretty confident with these kind of recaps of GCSE. Even when you're not given the original function, you can just go from the shape of the graph. So that's excellent. Right, we've got a reciprocal function here. And I spent a great deal of time yesterday in a drop-in session going through these sorts of ideas, because reciprocal graphs, although we sort of meet them at GCSE, they're a little bit trickier to understand. There's more going on. You've got this idea of an asymptote happening as well. But in terms of graph transformations, you can do it in very much the same way, obeys the same rules. We've just got to be careful with things like the asymptotes and how we deal with that. So how do we do this one? So we've got a sketch of y equals 3 over x, and then we want to sketch the graph of y equals 3 over x plus 2. So how do we go about that? So we want to state any coordinates where it crosses the axes, and also write down the equations of the asymptotes of the curve. So any suggestions here as to what's going to happen? What kind of transformation do we have going on? And I think this is understanding the link is a step up for some people here, because it's still the same rules, it's still transformations of functions, but these kind of graphs do confuse people because we're just not as familiar. Right, good suggestions coming in. Let's have a little look. Excellent. So the thing that's happening here is actually, I'll talk about the 3 for a second, because the graph of 1 over x as a sketch basically looks the same. Okay, the individual points are kind of further out or further in for 3 over x, but it still has same asymptotes at the axes. Okay, so the 3 isn't really affecting this too much. The difference here is the plus 2. And if I'm comparing it to 3 over x, so if I think of f of x as 3 over x, then the transformation I'm doing when I have 3 over x plus 2 is basically the x plus 2 is happening inside the function. So as some of you rightly suggested, inside the function, you kind of do the opposite to x. So this is going to move it to the left by 2. So what originally looked like this is getting translated 2 to the left. So we've got to think about our asymptotes here, and our asymptotes were the axes. It's not defined for the x and y axis. The graph never touches them. So if I now move it to the left by 2, it will touch one of those axes. So it's now got an asymptote where x is minus 2. So this is the line x equals minus 2. It still has an asymptote at y equals 0, or the x-axis, because I haven't moved it up or down. So that's fine. So the asymptotes are y equals 0 and x equals minus 2. But what we've got going on is obviously that whole shape has shifted to the left. So we have it moved over like this. And obviously there is going to have to be an intersection point here. So how can I find that intersection with the coordinate axes? How can I find that y-intercept for this transformed graph? I know the equation of it. How could I work that out? So I'll give you a second to think about that one and sort of make any suggestions. How could we do this? Excellent. And so for any function, don't let it faze us that it's perhaps something we're less familiar with sketching, or we don't like it as much, or there's asymptotes. To find a y-intercept, it is always just when x is 0. So if you sub x is 0 into this, that is spot on. That is how you're going to find it. We're finding the y value when x is 0. What do we get as the y value, as that point? So we know x is 0, and we're trying to find what y would be. So if I sub x in as 0, absolutely, I get y equals 3 over 2, or 1.5. So the y-intercept is 3 over 2. So what we've done is we've taken the graph, we've translated it 2 to the left, we've found where the asymptote has moved, and it's only affected the vertical one. I knew that the horizontal asymptote still stays as the x-axis, and then I found the y-intercept by subbing in x is 0. And there's loads of different transformations that you could do with these kind of graphs. So if I just give another example while we're on this one, how would it look if we actually were asked for 3 over x plus 2 plus 5? What would that do to this function? So we've kind of done half of this scenario, but imagine I tagged a plus 5 on the end now. So as a separate question, just while we're here, what would that do to the graph? Right, excellent. It would not only move it to the left, it would also move it up by 5. So this graph would then look like this. Excellent. Brilliant. So it would have an asymptote at 5 at y equals 5. So y equals 5 and x equals minus 2. So for that scenario, guys, could anyone find what this point and this point would be? So how would we do? Because now we realize there's actually going to be an x-intercept, a solution there as well. So we're going to have 2 values to find. So I've kind of added to this question and very well spotted that we've not only moved it to the left, we've also moved it up 5. And just looking through the comments, that's superb. So yes, so we can sub in when x is 0 and when y is 0. Brilliant. So if we sub in when x is 0, we're going to get 3 over 2 plus 5, which is basically going to be 6.5 or 13 over 2. So very well done to any of you that got that. And you could give it as a decimal as well. And when you sub in y is 0 to find the x-intercept, has anyone done that bit? So let me just do that now. So if y is 0, 0 equals to 3 over x plus 2 plus 5. I'm going to give you a chance because some of you might get there before me here. So hopefully we're happy to find what the x value is. It's the point when y is 0 and we're solving what x is. So we set it all equal to 0, rearrange and solve, and let's see what we get. Right, we've got some answers already. So if I move the minus 5 across, minus 5 equals to 3 over x plus 2. Times up, I get minus 5x minus 10 equals 3. So add the 10, minus 5x equals 13. So x equals minus 13 over 5. Very well done if you got that. Minus 13 over 5. And that looks right as well, because minus 13 over 5 is more negative than minus 2. So it ends up in the correct place. Let me just check I've done that correctly. I think that's good. Yeah, do we agree? Does that look okay? And does that method make sense? So I know I've kind of taken it a step further there than what the question was asking, but is that clear? Do I need to check anything? Yeah, okay. Quite a challenging one, but look at what you've just sketched. When you think about it, from just knowing what 1 over x looks like or 3 over x looks like, you've been able to sketch the function of 3 over x plus 2 plus 5, which, you know, if you were asked that at GCSE, would look incredibly challenging. And actually, it is just graph transformations. Brilliant. Right. Well done for following along with that, because I kind of threw another tricky question in the mix there. But it is essentially the same skills. So the same as if we were just transforming a cubic or transforming a quadratic or just a graph we don't even know the name of. If we can understand what the function and how the function is being transformed, it is kind of just matching points and sense checking the intercepts and the asymptotes. So that was really good. Excellent. Right, we're flying through the content today. So I'm happy to kind of sidetrack or answer any questions as we go. Because as I said before, this is such an important skill moving forward into year 13. And there will be lots of functions in year 13 quite quickly that we're very unfamiliar with. And we also need to be able to transform them. So that's hopefully a really good bit of reinforcing of this key skill. Right, here we go. So a function we perhaps seem more familiar with looks like a quadratic that we've got going on, but some certainly maybe even order polynomial. And what we've got is the points 6, 0, and 3 minus 1. So we've got this point as a minimum and these points as roots or solutions. And then we're asked to do y equals minus f of x. So this is absolutely a reflection, well suggested. So this is going to be a reflection of that graph that we've got there. And you might like to challenge yourself with some of these as well and think, could I actually define that graph? Do I actually know what that graph is? Like, could I give the equation of it? If they gave me those points, could I tell them the quadratic or the function? But anyway, this is asking us to do minus f of x. So what kind of reflection is this graph going to be? Is this transformation going to be? Because it's very easy to mix these up. And as we go on to some harder functions, and we have minus f of x or f of minus x, it's very easy to get it the wrong way round. Right, superb. It is a reflection in the x-axis, but some people like to think of it as the y values flip. But essentially, if the y values flip, then that's a reflection in the x-axis. So outside the brackets, you are doing the thing to y. So all the outputs are being multiplied by minus 1. And so they're flipping in the x-axis and becoming the negative versions of that y value and vice versa. So anything that was negative goes to the positive side. And well suggested there, Henny, I think I can see your suggestion of what the graph could be based on probably the roots from the sketch. So that's lovely. And thanks for suggesting that. And then when you think of timesing it by minus 1, you could also work out what perhaps the reflected function would be as a function. So that point there, absolutely, that minimum is now going to become a maximum. And what's going to change is the y value is going to be times by minus 1. So I totally agree. That would be at 3, 1. And it would be reflected like this. Oh, no, I'm not happy with that. I'm going to go from scratch. So sketch is obviously important that the shape is correct. And it looks sort of symmetric. So this point would be 3, 1. Absolutely. Now, obviously, when you times 0, 0, you times the y bit by minus 1, the roots stay the same. The solutions would be the same. So this one that is 6, 0 will still be 6, 0 because it's the 0 that would be times by minus 1. So the graph sort of reflects around the roots. And you know that that should be the case. And then obviously the turning points are kind of mirrored in that way. So is that clear? Is that something we're quite happy with? And obviously, again, it says on this one, and of any minimum and maximum points. And generally, something that I've stressed before, and I do stress a lot, whenever you're asked at A-level to do a sketch, we actually not only want the intersections with the axes, but we want the correct shape, we want any asymptotes, we want any turning points. How else can we find turning points? Had it not been a quadratic, if we were given any function, how else can you guys find a turning point? Because this is a big change at A-level, a big step up from GCSE. If I kind of throw any function at you and you're not even too sure on the shape, how could you find where turning points are happening? So obviously, if you're given the sketch, you can just see, you can kind of work out where there's one there, there's a local turning point around that value. So for excellent, so for quadratics, completing the square is a brilliant skill that allows us to find turning points. Also here, you might realize for quadratics that you can also use the symmetry of the roots. It's halfway between 0 and 6, you know, it's at 3. You could plug that in and get the output. What else? Excellent. Differentiation, that new skill we learn at A-level of calculus, allows us to find turning points as well. So for quadratics, we should have all sorts of skills because we're so familiar with how they look, that there's completing the square, that we can use symmetries, that we can use differentiation. But for any function, the method we employ for turning points is differentiation. We look at calculus and we look at the gradient of a function that kind of turns. So it would be a zero gradient at that point. Okay, so that's really kind of not necessary here at all, but it is worth knowing that minimums and maximums can be worked out, turning points and any gradients of any points along the curve actually. So really well done. So a little bit of a reminder of the other skills that could be asked to bring in. So generally what I'm getting at is when you're asked to do a sketch at A level, it's not like GCSE when they say plot and you do a little table of values and you put values and you kind of try and draw it nicely. You still want to make it look nice and A-level standard, but they're looking for key things. Do you understand the shape? Do you know where the turning points are? Do you know where the intersections of the axes are and what the general function is behaving like? So really well done, guys. That was great. Let's move on. So this question here, so we've got the following, and this is obviously an important condition. So I'm going to give you a chance to have a little think about this one. And it says on separate diagrams, so again, another separate part of the question, sketch y equals f of x plus p, where p is between 0 and 3, not inclusive of 0 and 3. So a strict inequality bounded at both ends. So basically it's between 0 and 3, but isn't either of those values. So what can we say here? What do we know is going to happen to that curve? Any ideas? So I'll give you a second to think about this because this is quite challenging, this one. Okay, and remember, it doesn't have to be an integer. It could be 1 or 2. It could be 1.735. So I think 1 or 2, it might be good for helping us work out like roughly what's going to happen. But they haven't stated that p has to be a whole number or an integer. So it can actually still be a decimal value in between 0 and 3. But we want to just generally get this sketch right. So it's still a very general sketch. We haven't got to like guess a value for p. But if you like picking a value, then just think, right, well, what would that mean about the sketch? What would all these sketches that fit that constraint have in common? Good, and the value p is important. So that's not what I'm not saying like forget about p. It is important, and it is important that it's in this interval. So how would I sketch it? It will move to the left. I totally agree. Because p is positive, then we do the opposite inside the bracket. So it will go like minus p. It will go p amounts to the left. Right. Good. So because p is less than 3, then what we know is that turning point isn't going to quite make it back to there. Okay. If it was 3, that would land bang on at the y-intercept. So what we basically want to do is kind of show that the turning point is still sort of probably happening in here, in this quadrant. But we are aware that this solution is going to move that way as well, this route, and this one is going to move that way. So I would sketch it probably like, not like that, because that's going to come out not very well. Probably using the turning point there. And how would I label the actual points with the axes? Like how would I label this, this, and this? And actually, maybe I don't need to worry so much at the moment about the y-intercept, but I certainly could label this turning point because it did ask us for any minimums or maximums and where it intersects the x-axis. So it didn't actually ask for the y-intercept. Right, let's have a little look. So I agree. I think the x-intercept we can literally just write as minus p0. So yes, you're right in thinking x minus p, but it's 0 minus p, which is just minus p. And this point here, absolutely, I totally agree with you guys, is going to be 6 minus p. And then the y value of that is 0. And then this turning point is going to be what? Superb. 3 minus p. And what's the y value of that turning point? So this point is 3 minus p. But what is the actual y value here? Any ideas? Excellent. The graph hasn't moved up or down, so superb. So it's still kind of, basically, it's still in line with that, but it's now sort of turning somewhere over here. So this y value is still -1. Really good. So that, and do look out for the question, because if you think, well, how do I know the y-intercept? For this question, it wasn't actually asking you for the y-intercept. It was just asking you for any places it intersects the x-axis or where the maximums and minimums go. So really well worked out. But it is worth doing that sense checking thing of, is that turning point going to kind of go past the y-axis, or is it still going to stay in that fourth quadrant? So that was probably, yeah, so a 4-mark question. So I would say the way the marks would be broken down for this would be probably 1 mark for the correct shape, knowing it stays the same way up and doesn't quite go through the origin. Another mark for having the minimum in the fourth quadrant. And then another mark for actually labeling these correctly, because it did ask you to label it, and we want it in terms of P. And then another point for labeling the value, like the coordinate of the minimum. So that was excellent as well. Any questions there or comments anyone wants to ask? Because this was I think, brilliant engagement there, guys, especially when graph transformations is quite a tricky one to kind of type in. So you've done really well there to kind of suggest points as well. No problem. So I think I'm going to just quickly talk through, just in general, where transformations go as a topic in year 13, and then talk a little bit about Snap Revise as well, so that you guys are aware of the other bits that we're sort of doing as well. So transformations, as I said, oh, I've got some questions coming in. This is lovely. So we don't have to work out the exact value of P. No, good question there. We don't have to work out the exact value of P, because it's just telling us that P is in this given sort of domain or set of range of values. How will it affect the sketch? And because 3 is not greater, P is not greater than 3, that point can't go beyond the y-axis. And if we know that, we know as a sketch, it's somewhere on this side. Okay. Obviously, if P could be anything, then that sketch could move left or right. It could be, you know, P could be a negative number and actually push it that way. So that constraint is for us to know, okay, it's going to move it a bit this way, but not enough to take the minimum into the next quadrant. Other questions we've got coming in. So why does it say on separate diagrams? Right. Good question. So I think they like to do this probably more in the exam, so that you can just kind of quite clearly label the points. Sometimes it will say on the same diagram to check you understand the relationship with the transform with the original function. But often they do separate diagrams just so it's clearer, really, because there's so much going on. They want to know you understand the key information, so they'll say on separate diagrams. And then another question, a horizontal stretch. Yeah, absolutely. So a horizontal stretch of this function. So if, for example, here, let's do that for this one. If, for example, we had this function and I said, right, f of, let's do f of 3x. Can anyone suggest what's going to happen to this if it was going to undergo the transformation f of 3x? Any suggestions there? That was a really good question. How would that look on a separate diagram? So I'll do a separate diagram for you guys there. How is that one going to look? You are going to divide the x values by 3. So telling me with reference to those 3 key points, what is going to happen? Superb. What is going to happen to that graph? Yeah, it will basically be a compression, like it will stretch inwards. I know what you mean there. It will kind of, the values will divide by 3. So 0, 0 absolutely will stay the same. 6 will move to 2. Okay. And that minimum that was at 3 minus 1 will now be at 1 minus 1. So it still keeps the symmetry, but it compresses it. So basically what it will look like is it will be like kind of 3 times compressed. I've done that looking like about a half. But the turning point will still be at -1. It will still be the same sort of value of the way down. but it will be just compressed and happening at a kind of quicker rate. So on the same diagram, you'd be able to see that a bit clearer. But that was a really good question, because the X ones are often the trickier ones to do. And are we all clear on that this minimum would just become 3 times smaller in the X direction as well? So it'd be at 1 minus 1, which is really useful, because obviously we know nothing's happening to Y. It's not being stretched or shifted in terms of Y. It's just being compressed in an X sense or direction. So superb question. I'm glad we asked about that. Right, modulus. That's a really good question. And this is actually what I spoke about in a drop-in on Snap Revise yesterday. The modulus is a year 13 topic, but it does tie in with graph transformation. So I'll quickly explain that to you now. No worries, I'm glad I answered that question there. For a modulus function, which is something that turns it positive and absolute values, brilliant. If you had, for example, this sketch, and I took the modulus of it, then you would hopefully be aware that any negative bits would reflect up. So it would now look like that, okay? So basically, if you have modulus f of x, where the modulus is around the whole function, that means the outputs have to be positive. So if you have something like this and you do the modulus, that's going to look like that, okay? If, for example, I did f of modulus x, what this means is that all the x values that were negative get turned positive first, and then that gets mirrored basically in the y-axis. So what that would look like is that would look like that, okay? Or for this sketch, that would look like, say, for example, we had a function that originally looked like this. The original negative values become redundant, and it mirrors the positive x values in the y-axis. So maybe if I open a blank slide, or I clear some of this, I can make more sense of it. But let me just clear this off. So the modulus is a topic you see at year 13, and I'm really pleased we've had questions on this, because actually this is kind of where this stuff is going. So basically, if you have modulus f of x, this means reflect any negative y values. Yes. So if it's, so you don't tend to write f of 3. I'll come back to the modulus thing in a sec. We don't write it like that. We would write it as 3 f of x. The scalar is on the outside. You do it to y. Inside the brackets, you divide by 3. So you wouldn't write it this way. You'd write it more like that. But yes, Thomas, that is correct. The scalar is affecting y just in the way it says on the tin. 3 times the y value. Absolutely. But if we've got a modulus sign, just in answer to that other question, that means reflect any negative y values up in x-axis. No worries, that's great, great question. And if you have f of modulus x, what this one does is reflect / copy positive part x part of graph in the y-axis. And I spent a lot of time doing this in drop-in sessions on Snap Revise before, because this is something you can practice really easy just from sketching in the y-axis. So if, for example, we had y equals e to the x, and I said sketch y equals e to the modulus of x, then what you would do is e to the x looks like this, but e to the modulus of x would basically, the positive bit would be the same, and it would reflect that here, because e to the -1 would just be doing what e to the 1 is doing. So this is like the inside the function one. So it copies the positive part of the graph in the y-axis. So basically the negative bit doesn't exist anymore, and it just copies what the positive x values are doing. Whereas this one just reflects any negative bits that are coming out for y upwards. So sorry for those that maybe haven't done this yet, this probably doesn't make much sense, but the modulus function is something you do in year 13, and it basically really builds on graph transformations. Essentially, the year 12 and GCSE ideas we've said today are comprised of mostly looking at outside the brackets, do it to y, inside the brackets, do the opposite to x, and that involves some reflections and stuff as well. A modulus graph deals with turning certain bits positive, and that's a function you see early on in year 13. That's lovely. I'm glad, hopefully I've cleared that up. But as I said, I do want to just mention how we can go through specific questions like this and tailor your questions, tailor answers to the questions you have, because that is something that we're kind of constantly doing on Snap Revise. So I'm just going to stop sharing that PowerPoint for a second. So hopefully you can see me again. And I'm just going to quickly show you kind of the schedule of what we do for this. So let me do that. Share this page, not that page, sorry, it's the same thing. I'm going to share the website, which is this one here. So let me know that you guys can see this. And on our Snap Revise platform, we have web classes, a bit like what you've done today, with some really carefully explained questions that come up on the A-level on all parts of the course, pure, mechanics, and stats, and also drop-ins. So as I mentioned earlier, this kind of modulus graph stuff I looked at in a drop-in yesterday because some students had some questions on it. So we can kind of go through anything you want in drop-ins, and they happen very regularly. And obviously on the platform as well, everything's sort of tailor-made to the different A-level courses. So there's loads of stuff for like diagnostic quizzes, really clear revision sheets, mock papers, and everything is designed in line with the new A-level. So please do check this out if you haven't already. And as I said, the diagnostic quizzes are great because they'll allow you the opportunity to kind of test yourself and see what you don't understand. And then it's all followed up with a really clear video that kind of you can jump to the bits that you struggled with, and it's all kind of color coded and nice. And there's exam packs, there's a revision guide on every kind of topic. So it's all broken down really clearly. And then obviously loads of these live sessions happening on the platform as well. So if you guys have got questions or you just want to kind of go over stuff from year 12, especially with everything being a little bit disrupted this year, it's certainly something worth checking out. And quick, snappy quizzes are brilliant as well on there. So have a little look if you haven't already at the Snap Revise platform. It's all broken down really clearly, as I said. But a huge advantage of it is, as I mentioned before, loads of these interactive sessions. And as you guys have engaged so well today, I think it is definitely something that you might be interested in. So what I'm going to do is if I share the following code, so transform 10, that will give you a discount for Snap Revise. So it might be worth checking out if you've enjoyed this session. Thanks very much to everyone for all your questions and comments. That's really reassuring to see so many people working through this, hopefully understanding the ideas and also asking about year 13 ideas as well. It's been a real strange time where people have had to just completely take ownership of what they're learning and push on. And I've seen that for a lot of students. So that's been brilliant. Really well done to all of you today. And as I said, there'll be more of these sessions coming up on YouTube live. So if you are enjoying them, please set a reminder. Make sure you tune in again. It's been lovely having that engagement with so many of you today. Some brilliant questions. And you're obviously all very keen mathematicians, so it's always good to see. That's fine, lovely. Thanks for taking part. That's been brilliant. So I hope to see you all at some point soon. But as I said, if you're interested in this code, make sure you make the most of that today. And as I said, more sessions will be coming up shortly on YouTube. So we've got the other subjects on there as well. Any integration or differentiation? Well, we've done loads of that on Snap Revise, and I'm sure there probably is a class coming up on YouTube on calculus. So I'll have another check because I don't know the schedule off the top of my head, but I would have thought that that's in the mix somewhere. I'll make a note and follow that up. But I think integration and differentiation are massive A-level topics in year 12 and 13. So that certainly would be a sensible one to have a look at. So hopefully, yeah, we can try and cover that at some point in the near future. But thanks for the suggestion, and I'm glad that you're looking ahead at that calculus stuff already, because it's crucial to the A-level pure content. So really well done. I'm going to stop sharing that there. Thanks very much again to everyone for taking part there. Keep well, enjoy the nice weather, and have a bit of a break as well throughout this half term. And hopefully things will be sort of back to normal soon, but it's great to see so many of you working hard. Well done. Take care, and thanks again. Cool.